So again, welcome to this presentation that is going to be developed under the task 61 for the wind task. And yeah, the title for the presentation is going to be like the modeling alkaline electrolyzer in digital real-time simulation environment and green integration. So yeah, so just let me present you a little bit of the agenda that I have prepared for you today. I will start providing some of the background about the electrolyzer, Power2X modeling, and why is digital real-time simulation for those who are not familiar with this term or topic. A little bit of the methodology overview that we were working, how we do the implementation in the digital real-time simulation, the case studies that we want to analyze that are two mainly. It's a standalone operation and a grid connected operation for the electrolyzer. I will share with you some of the simulation results that we obtained and the main takeaways at the future work that we want to do in this field, and we can conclude with a session of questions and answers. So, okay, so a little bit more about the background. I would like to let you know about what is the history between Power2X and power systems now, because now Power2X is starting to becoming a more common term for power systems and people interested in energy, sustainable energy for energy systems. So as we know, we have a current trend for a higher participation of the renewable generators for producing electricity, and this maybe will create a scenario when we at some point we will have a surplus of generation, and sometimes the generation that we can get from the renewable generators not necessarily match with the periods when we have a big energy or power demand in our power system. So what is one of the possible solutions that we are analyzing at the moment is what is called the Power2X. Inside the Power2X, we can say that we have a cornerstone element that is called the electrolyzer, which is using this surplus of generation or surplus of power for producing hydrogen, which can be used as a new energy for different activities, like for example, the production of biofuels. It can be using for transportation industry and even e-mobility. So, and it can be also storage. So this new energy source, it can be a little bit of a transversal new energy. Now we have some energy policies, especially in Europe. We in the last years are proposing that the electrolyzer can be included in the power system with big rated power capacities, which can become in key players for the power systems because of his power and also the power demand that they can require from the system. So that is why we arrived to this. What is going to be the role of the electrolyzers in power system? As you can see here, the electrolyzer can be defined as a flexible load that is going to be essentially trying to consume power from the bulk power grid of a country or system at some specific points. But also what is really peculiar from this new flexible load is that they are going to interact with the power grid through the inverted. So this is becoming an inverted base interaction with the power grid. This is a kind of, it could be really beneficial for the power system because the inverted base generation, for example, is reaching a point when we now are discussing that these generators can offer different kind of services for the grid. And this is why, for example, we are living this kind of boom for the grid forming capability, mainly in wind farms. So also it's really that this can be also beneficial because at the end we can also still use this kind of concepts for this new flexible load in our system. At the moment, even though that there are more electrolyzer technologies under research or close to be available in the market, we can say that there are two main electrolyzer technologies in the market. The first one is the alkaline electrolyzer that, at least for this presentation, it's going to be denoted as IL, and the proton exchange membrane electrolyzer, which is and also known as a PEM electrolyzer. There are some kind of differences between these two technologies, but at least for the presentation of today, we decided to go for the alkaline electrolyzer because even though that they have, for example, some constraints compared with the PEM electrolyzer regarding the current densities that they can reach and the slower run rates that they can offer, there are still the main pro for this technology is that they have a low cost and they can be more widely used in industrial projects that are already ongoing in the system. So yeah, but for understanding a little bit about whether the approaches that other research has been done regarding the modeling for the electrolyzer, we can say that can classify the approaches in 5 main categories, which, as you can see in this slide, for example, we have steady state. Oh, sorry, misspelling error here. But we have these steady state models, which, for example, are representing electrolyzer as a piecewise linear efficiency curves or just constant values of power necessities from the grid. And apparently it's a node for analysis regarding planning and dispatch. As a pro, they are fast and simple, but of course they are not considering the dynamic and the operation of the electrolyzer. We also have dynamic approaches, which mainly they are trying to analyze the dynamic behavior of the electrolyzer. It can be, for example, the characteristics in the variation in the time for the inputs and outputs of the electrolyzer, as for example, power, pressure, and different kind of temperatures. And which main application it can be for testing control techniques, stability, and grid services if we are in the power system field. And as I said, yeah, it's really good if we want to capture some time response from these models. We also have some researchers focusing on having an electrochemical modeling, which is essentially trying to capture all these electrochemical interaction during the operation of the electrolyzer. There are other people who are trying to combine this previous mentioned modeling approach. And recently, there are also some people trying to do some data-driven modeling, which essentially they are trying to get some measurements from electrolyzer already operating and trying to identify the main characteristics of the operation for having a model. At least for the modeling of methodology that you will see in the upcoming slides, we can say that we are kind of proposing a hybrid modeling approach because we are considering some of the electrochemical equations from the electrolyzer, but also we are trying to capture some of the dynamic operation from the electrical variables because we want to analyze the impact of the electrolyzer in the power system. So yeah, just a little bit of a brief explanation about what is the digital real-time simulation, because I am not sure what is the background of the people that join today for us. But the digital real-time simulations is it's a kind of software and hardware that is becoming useful for electrical engineering because it's letting us to emulate and modeling a real grid with a more security level, because essentially bulk power system can be modeled in a software and we can test some of his features in a lab environment. As you can see here, for example, it's typically composed by the workstation that is offering a key interface for the user. We have what we call the real-time simulator, which is essentially a multi-core high-speed computer processor when we can model the power grid, and which is usually mounted in a rack that includes a different kind of analog and digital input outputs. We can also have some amplified inputs and outputs because this kind of facility is giving us the possibility to interact with real hardware, and sometimes the outputs that we can have from the simulation part is in milliamps or millivolts, and that usually need to be amplified for being connected to real equipment. And also we have the possibility to interact with real communication protocols that are applied in power system for communication at substation level. For example, this DNP3 and Ethernet, so something like that. And after this, as I mentioned, this can be used for real components. At the moment, some of the real components that have been tested and considered are generators, mainly from renewable sources, as wind turbines and PV, and control for them. It's also widely used for protection devices, SCADA system, FACS, SBC, STATCOMs, and something that is gaining more attention now, that is the HVDC systems and the multi-level converter control. But since this kind of system is giving us the possibility to simulate different types of events in the power system, what is really important to consider when we decide to go for the modeling and using for simulations is to use the appropriate time step according to the application that we want. Here in this graphic, you can see the different type of event that we can represent using digital real-time simulations. And according to the dynamics of these events, we can more or less have define the tab step for our simulations. Yeah, so what is the main contribution that we want to do with this methodology that we are going to see now is that we are offering is to model the alkaline electrolyzer in digital real-time simulation environments, and mainly addressing the challenge of how to scale up the electrolyzers from kilowatts to megawatt rated powers, which is the nominal powers that people expect to have in power system in the near future. So yeah, just here a little bit about of the modeling and the scale-up methodology that we have designed for this. It's like, and we can say that we divide in two levels, and is developing two commercially available softwares. As you can see, for example, in the main part or in the app part, we have the numeric computation software that in this case is MATLAB. When we are going to compute some electrolyzer parameters, as for example the current of the cell, the ohmic losses, and the ohmic overpotential, what is going to be the voltage of the cell, the power of the cell, also what are the number of series and parallels that we need to connect for having a specific rated power in our electrolyzer plant, but also what are the levels of voltage and current that we want to have that. And here we have the input data that we need for these calculations, that at least in this methodology is going to be the current density, the temperature of operation, the area of the cell that we are going to do, what is the desired stack power that we want to have, and the stack voltage operation. the stack voltage and also the total electrolyzer voltage that we want. Once we have all these calculations, the user is going to assign all of these parameters and setting the proper elements inside the digital real-time simulation environment for the simulations and simulate the test scenarios that for our case is the standalone and infinity bus topologies that you will see a little bit more in detail later. And we finalize with the collection of the results. But for this modeling, for this methodology, sorry, we need to be clear about some assumptions that we are doing here. For example, we are considering keeping in mind the constant thermal mass because we need to ensure the energy balancing at every point of the simulation. We are neglecting the dynamics in the mass transportation. We are considering this as a one-dimensional model for avoiding computational burden during the simulations. Also, we consider the gases as ideal gases and following the uniform gas distribution. We are also considering that the pressure through the stack and the cell area is uniform. And yeah, since also we want to maybe in the future do a power hardware in the loop validation, we are keeping the feeding voltage for the electrolyzer up to 450 volts, which is a value typical that you can reach in a lab facility. Okay, so now I'm going to explain a little bit what are the equations that we use in the add part of the methodology. We have designed this in a way that we are starting at set level and we can finish at plant level or the bigger electrolyzer size. So once we have the input variables that you saw, we are going to calculate the cell current, the cell voltage, or the cell power. Once we have this, we define the number of cells in series, which is an input for computing the stack voltage. So yeah, when we refer to a stack voltage, it's like a kind of combination of different cells inside of the electrolyzer units. Once we have this stack voltage, we compute the number of branches in parallel that we final plant is going to have. We finally compute the plant current and the plant power for the operations. So most of these equations that has been widely used in the literature review, and here you can find some of the main sources for these equations. Yeah, once we have defined all the calculations and the parameters, as I mentioned, we need to implement this in the environment of the digital real-time simulation. For this case, we are using the AirSCAD FX software. Inside of that, we can have a alkaline electrolyzer stack like this. Now this is a default element in the software, but which still need to be assigned all the different variables that we present in the methodology. How we are doing these assignations of variables is we are using these draft variables inside and defining some controllers for that. Inside the software, we have two main environments. One is the draft environment and other the runtime environment. The draft environment is the space when we can design or circuit or topology of our system using the default library elements. And the runtime environment is when we can put the different controllers for controlling different variables and also push buttons for controlling the sequence of the simulations. For this scenario, we are with the idea of us is just to verify the standalone operation of the electrolyzer stack. Why we are doing this? Because we want to verify the cell characteristics of the electrolyzer. As you will see later, why is this important? And for this simulation, we are also considering that the electrolyzer is operating a constant temperature and the electrolyte that we are using is potassium hydroxide in this case. The second case study is going to be now the connection of the electrolyzer to an infinity bus power grid. Here we have a thyristor-based converter coupled with the power transformer. Once again, inside of this green box that you can see here, we now decided to implement different type of controllers now. For example, we have a thyristor-based converter, as you can see here, but also we have current control in this converter. We also implement some water control and temperature control for the electrolyzer, which is going to let us to keep the water flow rate, the desired levels according to the set point, to the power set point in the electrolyzer. And also for that, we also need to keep the temperature according to a reference point during this operation. Again, you can see the draft environment and the runtime environment inside the software. So after this, we can see the simulations. As I said, for the first case study, when the electrolyzer is operating as a standalone unit, what we want to verify is the polarization curve. Why this polarization curve is important is because when we want to operate the electrolyzer connected to a power system, there are some really big interest in that the electrolyzer can maybe offer any kind of service to the grid. And for doing that, and also for keeping a safe operation of the electrolyzer, we need to be in the ohmic polarization region of the electrolyzer, which is this kind of linear part of the curve. But before to reach this region in the curve, we also need to overpass what is the activation polarization part of the curve. Also something really good from the electrolyzer, for the scaling up electrolyzer that we are doing here, is that compared to some papers doing modeling, we can also verify that the activation polarization curve is according to the defined regions for alkaline electrolyzer, which is a little bit up to 1 voltage, 1 volt. And also here in this table, you can find the different parameters that we are using, and we are scaling up for the different three rated powers that we are trying to verify in this research, that it was 100 kilowatts, 1 megawatt, and 1.5 megawatts. So now that we have what is the polarization curve for this electrolyzer, we decided to connect the electrolyzer to infinity bus, which is going to emulate the connection of the electrolyzer to a power grid from where we are going to start drawing some power. So here the simulation sequence is a little bit easier. At around 0.5 seconds, the breaker is closed, which means that the electrolyzer is connected to the power grid, and that is why we have here this peak, which is mainly showing that we start now consuming power from the grid. At second 5, more or less, we changed the reference, the set point of the set point for the power consumption to 0.5 per unit, and we can see why the electrolyzer start to decrease his power consumption. Here in these plots for the 3 different rated powers, we plotted the power consumption for the electrolyzer, but also what is the power requirement in the grid and the converter side. As you can see here, for the 3 different rated power, they are more or less keeping the nominal powers that we decided, that we defined for the scaling out methodology. But we also noticed that they are in some cases consuming a little bit more of the of the rated power that they are designed. What is that? It's because as you can see here, we are just trying to keeping a simple power electronic topology. If we want to avoid that and keeping the electrolyzer close to his rated power and also rated voltage, we will need to include some extra electronic equipment, as for example a bus converter before to the connection. So, but in this case, we more or less wanted just to taste for methodology and see what is going to be the interaction for the power grid. So we assume that it's quite okay. Also, another aspect that we want to evaluate during this operation was what is going to be the efficiency for the hydrogen production. And here we can see that for the three electrolyzers that we are testing, the average hydrogen production is higher than 90%, which is also suggesting that the need of having a more detailed power electronics modeling is required in these cases inside the software. Yeah, so just for finishing, here is the summary of the main takeaways and the future work. I would like that you keep in mind that we are presenting a scalable modeling framework, and this proposed framework is for alkaline electrolyzer, and it's doing in a kind of a modular way, because you can start it from the cell level and going until to the stack plant level. And this is kind of ensuring the reusability and scalability across various levels and configurations that people can want to test in the future. We also are integrating into digital real-time packages, which are allowing to doing some more kind of detailed power system analysis. For example, you can analyze the electromagnetic behavior or response when you connect this. We also do a kind of testing performance for three different rated powers, 100 kilowatts, 1 megawatt, and 1.5 megawatt, and the standalone operation, and also connected to a grid. Of course, we also have some current limitations in the models and results that you can see, and is that we are presenting a simplified converter topology. These results are not experimental validate, and we have not considered any kind of financial or cost for the electrolyzer and the grid integration. So whether the future work that we spend is going to be just refine this the converters model using for the simulation, adding maybe, as I mentioned, another kind of type of converters. And this also maybe still pending to do a verification with power hardware in the loop. Just before to finish, I would like to give my thanks to the collaborators that helped me with this research. From the DTU side, Tushi and Tillman, and also people from Entrail, that is Kumar, Richard, and Steve. The people who are the foundations who allow to do this research together, and my visit to Entrail during the last part of the last year and the beginning of this. And a special thanks to the Energy System Integration Facility, ISEF at Entrail, for the resources and the support. So yeah, thanks for your attention. I hope that it was not really long for you, and we can open the questions part if you have.